Right. The technology always lags behind.
Which one? Those two ones. No. That's it. Go.
I'm just
That's all. That's it.
yeah.
Come on, tell me.
Okay, welcome to I Can't Believe It's Chemistry, and I hope you find the experiments today to be interesting and maybe a bit different than the experiments you'd normally do in school. We're going to kick things off, and we're going to start off with Gemma and Sinead, and so we'll go to.
Well, before we start, what do we need? I feel like John had never let us into a lab without our lab coats on, so. Start blowing a few bubbles first.
Ah, yeah. Blow a few bubbles.
Do you want to try and catch them?
Yeah.
Alright,
Go.
go.
Okay. And catch some.
Now, do you want to put a bit of water on it? See if you can catch them with a bit of water.
Go down. Shit, this isn't working. It's not going to work.
Well, seeing as how we're doing combustion, Gemma, why don't we just try and light them?
Okay, try and like that.
Have you got the matches then?
Not yet. See somewhere? Yeah, okay.
We can try and light that little one that's there. Okay. Not really going to happen there. Do you want to get a volunteer for 6 seconds?
Yeah, we get a volunteer. The girl at the back?
Yeah?
Do you want to go? Just have to make some bubbles first.
Okay. So we're going to make something now that's going to make a few more bubbles, hopefully, for us. Okay. So can you just fill that with a bit of water there, please? Yeah, just a bit of water. That's grand. A bit of washing up.
Plenty of us make plenty of bubbles. Keep going.
I just want to put it in there, be generous. That's good. That's good. Now, we try and use that instead of just blowing bubbles.
Ah, yeah. I think it'll save me blowing into it. I think we're going to need more water out of it.
I think we're going to be able to do that. It's combustion, so what do you think we can do? You try and light them again? Yeah, try.
Well, I think we need a few more.
A few more on there.
Plenty of bubbles. Bit of wash up it.
Ready, Sinead? Yeah. Okay, go on to other job. Try and light it. Okay, so you need more.
Did you do the bubble first?
Yeah. Right, touch that down there and make it. Oh, look down. Got a ruler there. Yeah. Gives a ruler. Right, you just catch it on a ruler. Okay. we light it? Yeah. Woo! Did anyone think why that burned and the ruler didn't? We didn't burn the ruler, did we? No, we didn't burn the ruler. Does anyone know? What do you think? What do you put into the water? Any ideas what we put into the water? Maybe what, gas? Yeah, we put a gas into the water, yeah. So what do you think was it that burned? Was it the water or the gas? The gas. So the water, you see, made a seal around the ruler and that stopped it from burning. So, okay. See, I think probably in Amy having a bit of a problem over there, so we let them go ahead.
I think we have a bit of a problem here. We have some potassium and some sodium. We're stored in some kind of wire. I want to know if we store it in anything else or what do we do with it? What do you think?
It's only give you safe to store in air because it's in a container for a reason. Does anyone have any ideas what we could do?
Maybe throw it into some water and see what happens.
It's sodium and potassium. So what do you think? Should we put it in some water and see what happens?
Might as well just throw it in, sure.
With no carbon. I'm just giving it a swish around so that it won't stick to the side of the glass.
Well, stir now.
Right, I have a little bit of sodium here. Just throw it into the water and see what happens.
I'd have to see more than that.
It fizzled and went around, but didn't do much. Will we try and do the potassium and see what happens?
I think you need a bigger bit of time.
We need a bigger bit as well. It's still fizzling in there, but it's not doing much.
So, if it fizzes in the water then, can we store it? Do you think we can store it in the water or is it not safe?
Must be safe.
Safe, so.
I'll try the potassium.
What do you think will happen when we put potassium in? It'll explode. It'll explode. Wishful thinking that I'm not leaving.
I hope not. There's a big piece of potassium.
We have a bigger piece of potassium.
So, yeah, I got it. Anyone can tell me where to see sodium or where you normally see sodium? Other than street lights, it's the classic street lights. We'll just throw it in here, we'll see what happens. I think we can take from that we can't store potassium or sodium in water, and there's a reason why it's stored in oil, and it's to keep it away from any moisture in the air and to stop it oxidizing in the air as well. So
if you come across it, dump it in the air because it's stored in oil for a reason.
it's very reactive. Okay, thank you. And I think Gemma has a bit of a setup with a candle here. Let's see what Gemma's doing here with the candle.
Yeah, need a bit of water. Have to have a smaller container.
Here, Gemma. Gemma, light us.
Thanks very much. We have one here as well.
Yeah, can we have one here?
Yeah. That's
Ladies, get one of the pinks up, Gemma. Get one of the girls up already. Alright, so, one of these.
What day?
What day?
That day. Don't worry, you'll all have a chance.
Thank you.
Oh, yeah.
Yeah, thanks.
Bit of encouragement. Have we got a pair of glasses for the rest?
You got a laptop for him? Look.
This is dangerous.
Okay.
I'd be okay.
Do you want to collect it?
Yeah.
Stick it up, just stick it over the hand first.
Oh, yeah. Okay, take it out and just block over the top. Yeah.
Now,
Now,
what do you think?
what do you think might be in that container?
CO2.
CO2. It's one of the products of combustion, isn't it? So,
How did we know it's CO2?
Sorry, that was my mistake.
right. Convert it over. Oh, damn it.
You might want to do it again. We're gonna have to
We'll
do more.
try it again. So just
Techniques aren't great.
like that.
Look at that. Genius.
Yeah.
Get it towards
So-
one more.
Don't pour this in.
So I'm going to take it off very quickly and you're just going to pour a little drop into it. It's not going to be too. There you go. Just pour a little drop in. Around yourself.
What's going to happen now?
What's going to happen to the lime water? It should happen to the lime water. Back turn. No change. Yeah. Like, you see that clear in there? And that's it's a milky kind of a colour that you described. Yeah. So that's milky. So that just shows there's carbon dioxide given off by the candle that's started combustion. So just try that.
So I'll see what's happening there. See the water starting to rise up at the. Does anyone know why the water's starting to rise up the cylinder?
Or get soaked up the cylinder. What did the candle use up when it was burning? Oxygen. And so the oxygen gets used up and sucks the water up the cylinder. And what percentage of the cylinder do you think the water should rise up? Or what? 7? Or 20%, yeah.
And why do you think it's 20%? That's the amount of oxygen that's in the air.
Richard, a bit of a bet on with.
We do, we have a bit of a bet on the Sinead here, so
Yeah?
we'll see what happens there.
Take off.
Yes. Okay, for this experiment, you need one rich city slicker, Sinead, and one poor country boy, Tommy.
Big farmer from Kilkenny.
Now, Sinead, being a Southsider, of course, has loads of money. Okay.
Ooh, Southside.
So she said she's going to burn cider with She has so much money, she's going to burn it, okay? And Tommy
Show me the
said
money.
he's a poor country boy, so he'd gladly take the leftovers.
So we actually need to put our money where our mouth is.
Come on, Sinead.
Okay.
Now, can we just hand that into the audience to make sure that it's a real 5 cent or €5 note? And we want it back.
They might be Northsiders.
It's okay, Ken. It's okay.
We're all happy to read a £5 note.
I think it should be a
€5, Ashka.
That's all she gives us.
Not that common.
So you want to burn them
So
up.
you're ready to use one.
I'm confident that you won't.
Okay. So we'll give it a little treatment first, will we? Just make sure it burns.
Just make sure. Like, dip the whole lot in, get the whole lot in
Begin the lights.
Okay. Think about your €5.
Go on, let it burn.
You wait until
We've agreed that Tommy can have the remains, seeing as it's a poor farmer. Okay, right? Oh no.
Sinead, it's all over.
Oh no!
Why didn't it burn? I already said he could have it if it had burned.
I'm afraid Tommy's €5 richer.
Can we see that it didn't burn?
Can everyone see? It's still intact.
Do you want to show you? Can we do it again?
Do it again.
Okay, can anyone tell me why we still have our €5?
Alcohol.
Very good.
Very good.
So the flame was from the alcohol. We have a mixture of alcohol and water in this. And what you saw burn was the alcohol, and the water coated the £5 note, which kept it below the ignition temperature of the paper, so the paper stayed intact. So Tommy.
There you go. Hey. Tommy's buying
I can
lunch.
speak to Kevin.
That's it from our group. Thanks.
Yep. Which one was it? Yeah. Dry ice cream.
They're up for after they're
Oh, that's the wrong one.
No, they're not using that.
They're not using that either. Right.
There we go. What's it like? See a picture of you after.
Sweep the crowd. Hey. There you are, Ken.
Okay. Hi, my name's Nicola, and our group, this is my group here, and what we're doing is some demonstrations on is just some of the properties of gases to do with pressure. Just gases and pressure is our main topic. To begin with, I'm going to start with some dry ice. Does anyone know what dry ice is? No, it's not water. It's solid carbon dioxide. So it is. Carbon dioxide is usually a gas, but here we have it in its solid form. That's why we were waiting for it, so to make sure, and we have to go straight away because it'll start melting, and then we won't be able to use it. So, as you can see, it would freeze my hands if I touched it, so I have to have gloves on, and it has to be kept as cold as possible, or else it will start. Okay. This is it's smoke machines. Sometimes they use this because it's not as toxic as using like actual smoke when they're making it and doesn't smell as bad. So just throw some in there. Okay. The explanation of why this happens, as you can see, I put in a solid and I'm getting gas straight off. What do you call that? Yeah, exactly, sublimation. It doesn't turn into a liquid at all. It goes directly okay, so what I'm going to do is, I have a beaker here of ice cold water, and I have a beaker here of hot water. Okay, now, what is the difference between these two beakers? Sorry? Yeah, which one's smoking more? The hot water. Yeah, exactly. The actual
hot water is melting.
Okay. Any more ideas? Okay, I'll tell you. Right. Some good ideas there. What actually is happening is there is a heat energy in the water because it's very hot. Okay. What's happening is the molecules in the solid carbon dioxide, okay, are taking the heat energy from the water. So obviously the hot water has a lot of heat energy, and are turning it into kinetic energy. And we know that gas has a lot more kinetic energy. It's wider spaced out. It can hit off each other a lot more. So there's a lot more kinetic energy there. So the heat energy is turned into kinetic energy. So the hotter the water, the more gas we're going to get off it. As we've seen, cold water really doesn't do much at all. Okay. So that's what the rest. Just this is explaining it in a molecular form. You can see dries in hot water when it sublimes. These are up here, and there's way more kinetic energy involved there. These ones are not hitting off each other at all. So when it goes into a gas, because it takes heat energy from the water, there's loads of kinetic energy, and it just goes all over the place like the gas. Okay. Next we have. We have Helen and Imelda, and they're going to do some experiments with just a bit of pressure, okay?
We have to do a bit of a maneuver here, so
All right.
now here we've got a balloon, just full of ordinary air, same as the air in the room, and it's full of little molecules of air, and all the molecules are pushing out, and all the molecules with the air around us are pushing in. So they're just even now, pushing out and pushing in at the same rate. It's not getting any bigger or any smaller. So inside that, it's normal atmospheric pressure. You've got all the molecules pushing in. Now hopefully this will work. Put it on. Turn it on. Now you can see that the air has been sucked out. We've got an overhead there to show. The air has been sucked out and all the molecules have been removed. This has sucked all the molecules of air from outside. It's still got the same number on the inside. And they're still pushing out. They've still got the same energy, but they have less pushing back against them. So they've got expanded the balloon. They're winning. They're pushing out. And when we let the air back in, what do you think will happen? All the molecules flying back in and they'll push down and squash down. Do you want to see that again? Yeah. Quick up and down. Air sucked out and back in again. Do you want it to burst? Yeah. If it bursts, it might suck it in through this.
Alright, give it a go.
No, it's blocked. It's blocked. But it's huge, isn't it? See, all the pressure depends on the number of molecules inside, like in the last experiment, the number of molecules and how fast they're moving, how much energy they have. But they didn't have to change in that case because the ones on the outside there are less of them then because there's less pressure. You know what these are? And they're full of little sugar. and the sugar is like the rubber in the balloon, and it makes bubbles, and the bubbles are full of air. You can squash it. And they're all fluidized marshmallows. What do you think will happen when we take some air out? Who likes big marshmallows? Okay, come on up and have a big marshmallow. Watch this. Sorry. Yeah, you can see it there. Now, again, all the little bubbles are expanding. They're like tiny little balloons, all expanding. Will they? Oh, wow. They look lovely, don't they? They look gorgeous. Do you love one? We'll have to take the lid off. Take that one. I know we can't. Sorry, we can't. It's been in the lab, so save for safety reasons.
That's terrible.
If you want to get a giant marshmallow like that, you'll have to go up in a balloon up into the upper atmosphere where the pressure is less and your marshmallows are huge. Now, in this we've got some cream, stored in whipped cream, and again it's full of little air bubbles. And Imelda loves doing this, so we have to do loads of things like this. And she loves cream. And this cream came out of one of those little aerosol cans. So it's held up very high pressure inside. When you lift it out, it just expands. Oh wow. That was just great. This is another little part to this. When a diver goes down to the bottom of the sea, right, the pressure is huge. All that water is way down on top of him or her. And nitrogen dissolves in the diver's blood. And when they come back up, the pressure is relieved on them. And what happens? Little bubbles, can you see that? Loads of bubbles form. The nitrogen comes out of solution and forms loads of bubbles, and that's called getting the bends. And it's very, very serious, you can die of it. So the only way to treat it, I mean, how much more serious can you get? The only way to treat it is to go into a decompression chamber and increase the pressure, get it back into solution, and then decrease the pressure very, very slowly. Right? And next we have Aileen. This is great fun, we love this.
These are my volunteers.
I'm sorry about the marshmallow. The tones.
Now, hello one and all. Today, I'm going to talk about more atmospheric pressure, basically. Can I have 2 volunteers? Preferably someone very strong and someone not so strong. The gentleman up the back there. I think he's no, yeah, you. Any girls on the phone? Anyone? Okay, I'm just going to pick the person closest to the edge. So the girl in the shirt, just wearing a shirt, no jumper. The girl that's turning around. Hey, go on. Okay, what you have to do is just hold the can either side as you have it, okay? And I want you to crush it when I tell you, okay?
This is a race.
This is going to be a race, and I'm going to use my one hand. You can only use one hand as well, so I'm cheating.
Can we use our foot?
No.
My head.
Actually, 2 fingers, and I'll just use Okay. Okay, when I say go, I'm going to see who can crush it first. And I'm going to win. I know I am. Okay? Yeah, fingers crossed. Okay, 1, 2, 3. Okay, I think what's happened here is, okay, who won? Okay, if you can do yours 2 there, I'll see if I can do better. Okay, thanks very much.
They're
Do you want burn? Okay, it's not going to work. What is supposed to happen is you've got a Coke can filled with a small amount of water. Okay, so can anyone think what's happening? What should have happened when I inverted the can? The water, okay, but if I was heating the water, what would have happened to the water? Yeah, so we have lots of steam, so if I have my fellow colleagues here to demonstrate what's going on.
Okay. There's lots and lots and lots and lots and lots of molecules. I could get you all up here to do this, but it'd be a bit too dangerous. There's lots and lots and lots of molecules in the water, okay? So what's happening is, if we heat up the water, what do you think is happening to the molecules? They not quite rise to the top. They, what do you think they're doing? Yeah, they get really excited, right? They start bouncing off one another.
I'm leaving the can.
So basically, when someone gets excited, one more person decides to jump off, and everybody else does. Leaves the can, basically, okay? So what's happening is the water's getting all heated up, and it's going into steam. So where does the air that was in the can go? Out. So how does it get out? Through the hole. So yeah, they're all cans that are open. So the air goes out through the hole. Now the reason that this didn't work was when the water in the can gets hot, it gets excited. The molecules all jump around inside the can. They expel all the air out of it. So then you're just left with steam. Okay. So what's outside the can that's not inside it?
Colder.
Well, if it's heated, what's inside the can? Hot. Steam. Okay, so outside the can there's loads of air. So basically, as we're talking about air pressure, outside the can, all the molecules that are outside the can decide if they want to crush it. Okay, so when we inverted that, it should have gone crush. But the air was, or the water was getting all this energy from the heat. But these obviously haven't taken off the boil, I had to plug it out. So they're not very hot. And when we inverted them, they should have just made a big bang and collapsed. Bang and collapsed. But the water was, the can wasn't warm enough and the water was perfectly cold, but it didn't take all the energy from the molecules, so it didn't collapse. Okay? And did anyone see, what would happen if you closed the top of the can? They explode. Has anyone seen the episode of Simpsons? Homer had his beef cans on the barbecue, and what happened? Kaboom! Okay, there you go. That's the experiment that didn't work.
As Aidan said, I am Enda, and I'm going to be making the hydrogen peroxide tonight. First of all, does anybody know what you use hydrogen peroxide for? Hair. Hair, exactly. What does it do to your hair? Exactly, it bleaches your hair. And you know that's really what actually happens when it bleaches your hair? Yeah. So it oxidizes your hair, doesn't it? Which leads us to oxidation. It oxidizes the hair, it tells us there should be oxygen in it, doesn't it? So, most of us already know the equation for hydrogen peroxide is H2O2, yeah? So we know it decomposes to give us water and oxygen. Tend to wash it up and give it a better effect. Now, I'm just going to bung in some blue food colour. I don't actually know what it was in, but hopefully it'll turn blue. Right, so, for this we're actually using, we're going to use a catalyst which is called potassium iodide. Does anyone know what a catalyst does? Speeds up the reaction, exactly. So, potassium iodide in this reaction is just a catalyst, it's not used up at all, speeds up the reaction. So, as you can see, get a nice thing. That's our John and our next speaker, now we're going to be doing polymers.
But tell you what, if you give me a nod, right, I'll be watching everything anyway. So, would you look well, yeah? Haha, right. I'll try and hide it. Yeah, I'll be able to switch over to that.
You're not getting it. You don't take photos of me.
So,
Okay. Okay, now you've seen the two groups. Our group is group 2 and 3. I'm going to do polymers. But before I start, does anybody know what a polymer is? You know what the word poly means? Very good, Lorraine. The word poly means many, and as I explain now, if you can rub the...
just keep using your slideshow.
That's the last one.
Yeah, this is, if you just concentrate on this. So a polymer is formed when many molecules of one or more different compounds come together to make a long chain. So when you think polymer, just think long chains, like thousands and thousands and thousands of molecules linked together. As you see, the red dots over there we can say is one monomer, and the triangles are another monomer. And they come together to form this long chain, as you can see in the bottom. If you want to go, yeah, go next slide. Now you can give me the slide so on everyday use, or have you ever seen polymers? Or well, I can go through them. Insulation, they're used in. It's very useful in insulation. As you can see, the boards on the top there, they're polymers. Any kind of plastic, that's polymers. They're all over the place. Nylon in clothing. If you look at your tag in the clothing, you might see nylon, like a certain percentage of nylon in your clothing. Plastic pipes, gutters and stuff like that. The next one's quite interesting if you're interested in recycling or environmental issues. A company called Wellman, who are based here in Ireland, in Mulla, County Cavan. They recycle plastic waste. They can actually make quilts and carpet fibres out of actually plastic bottles. And they've now got to the stage where they have too many plastic bottles, so they're giving them back to Coca-Cola and companies who can make plastic bottles again, which is quite interesting. Oil and petrol are other sources of polymers, long chains of hydrocarbons. So with all that stuff gone, Alice is going to do a demonstration now with polymers.
Hello everyone, as Dave said, my name is Alice, and what I have here is a 5-litre beaker, okay? And what do you think the substance I have in it is? Is what? What do you think it might be? It's kind of a squidgy material. Foam. Yeah, it's a type of foam, okay? Do you ever hear of styrofoam? Yeah? Right, what do you think styrofoam is mainly used in everyday use in houses? Packaging, exactly. For your televisions, for your video recorders so that they don't get broken. It's also used in insulation, keep things warm. So you have your Big Mac. What do you think your Big Mac's made from? Polystyrene. Or Big Mac. Okay, so styrofoam has a lot of different uses. Now, the question I want to put to you all, I have a smaller beaker here, okay? It only takes 800 mils. I want to see, can I make all of this styrofoam disappear into this beaker? So, do you think I'll be able to do it?
No.
Okay, hands up who thinks yes. Okay, we have a few people, yeah, and hands up who says no, not a chance. Okay, well most people are saying no, so Debbie here is going to give me a hand, and while we're doing that, Dave's going to go on and show another use of styrofoam.
Okay, as Alice has already pointed out, everybody knows what this is, yeah? And have you ever seen this stuff before? And this is styrofoam, which is used in installation. Yeah, like anything we ask people in the class what they usually go, yeah, that's what the white crumbly stuff. It is. So you can see you can break stuff off. So it is the white crumbly stuff. But if you think this is really brittle, then I think you could break it.
Yeah.
Right on So, not great. So what I'm trying to demonstrate is that it's really going to compression. We don't have any people from Cal here, besides Brian, no. But we all know how bad Calvin roads are. And they've actually used this stuff to fill up holes. They've actually found it better than stones. Like if it's a big dip in the road, they've dug up the road and filled it with this stuff. And it's helped solve, you know, the dip. I was going to, does anyone want to touch it? Is it being warm or cold?
Warm.
Warm? Why do you think it's warm? And why? Yeah, it is an insulator.
You were standing up, you were jumping on it.
You know, do it's made up. Yeah, very good. Right, it's made of air, and air is a really good insulator. So this is what this is how your house is built. The outside walls or most buildings. If your outside wall and your inner wall, and just behind the inner wall is this stuff called styrofoam, which helps insulate your house. So I'm just going to pass it back to Alice to see if she made this stuff disappear.
Okay, you doubted me. Alright. Well, as you can see, I took all my styrofoam from my large beaker and I could fit it in. Now, I didn't make it disappear, right? So the people that said it didn't disappear, you're right. But I did get it all in. Now, what happened? What do you think happened that made it dissolve?
There was acetone on there.
Acetone. Okay, I use a substance called acetone, okay? And as you can see, it's still a solid, but it's a squidgy kind of material. I can bend it. It's like dough, okay? So what happens? The acetone, styrofoam is made up of a lot of air. That's how it's used for insulation. And the air, the gas that's removed, the acetone removes it. So I have the same amount of material, but what's after happening is the volume of it is after totally compressing. So I have this tiny substance that I can fit into this beaker here. Okay? So if anyone would like to feel it, you can put on a pair of gloves and touch it at the end, okay? Yeah, I'll pass it on to Debbie and she's going to do another demonstration with you.
Okay. As I said, my name is Debbie, and I'm going to do my party trick here, okay? I'm going to put water into one of my cups, one over here. Okay, now I want you to keep an eye on this cup, and see, can you tell me where it ends up? Okay, does anyone know where it is? Okay? Wrong. Right. Let's try it again. Okay, I'm going to put it into this beaker over here now, which is different. Okay, I'm going to... Which one? Which one? Okay. Alright, I was cheating. There was something in the cups, right? What it was a polymer called sodium polyacrylate. Okay, I'm going to try it in a clear beaker, hopefully it will work again. Okay, that's what was in the bottom of the two cups that I put the water into. Okay, it's a super absorbent polymer. So when I pour the water in, you should be able to see that it absorbs, sort of. Yeah, it absorbs all the water. Okay, so that when I turn it upside down, the water doesn't come out. It is the
polymer, the sodium polyacrylate absorbs the water by a process that's called osmosis. Okay? Can anybody think of an everyday use for napkins? Very good. So I actually ripped open a napkin earlier. Nice. And that is the sodium polyacrylate is in there. And I did do it. I did take it out and I put it into a cup and put the water into it, but it isn't actually as absorbent as the stuff I used here, but it didn't work for a while. Okay? So that's another use of polymer. I'm going to pass you over to Mary, who is going to make nylon.
As Deborah said, I'm going to make nylon. So Dave said earlier that there are lots of uses of polymers, and we're going to show nylon today and how you might make it. Basically, nylon is a polymer which is formed when many molecules from two different substances come together. So we have two different substances here. This is just a quick demonstration. Compound A, which is silver paper clips, and compound B, which is gold paper clips. So if you just put them into a beaker, you should see that when we take them out, we'll actually get a chain forming. And that's exactly what happens with our nylon. You can see that there's gold, which is compound B, and silver, which is compound A, and they join together just like a chain. So we're just actually going to do the experiment now, and for the first compound we're going to use hexamethylene diamine, we're going to use as compound A, and we're going to use adipic chloride as compound B. I'm actually going to put on our gloves and our glasses because they're actually quite nasty chemicals. So. Yeah. Oh, yeah. The first one we're going to add in is the hexamethylene diamine. So we're just going to add 3 centimeters cubed. It's actually 2 centimeters cubed. And now we're going to add some food colour. We're adding the food colour because when the nylon is produced, it's actually white in colour, so just so you can actually see it better, just going to add some red food colour. And now we're going to add the adipic chloride. It's just going to add the same amount, which is 2 centimeters cubed. Now what should happen is that we should get a thin film forming between the two liquids. Now you can't actually see it there because of the food colour, but what happens is the two, as we did in our chain there, we'll have a molecule from the adipic chloride and a molecule from the hexamethylene diamine, which will join together to give us a thin film, which is actually a nylon polymer. So we're just actually going to try getting it out of it, which is actually quite tricky. So hopefully it will work. But that is, it's really hard to get it out. Okay, look. It keeps breaking, so.
It's breaking.
That is actually a nylon there. It did actually keep breaking. It's kind of hard to get it without breaking. That's actually nylon there. That's just our nylon forming. So I'm going to leave it back to Jada.
Now, for our next one, I'm going to select 4 volunteers. And I want people that will participate and do what we tell them, because you don't know what we're going to get to do on me. Okay. I think those 2 lads, do you mind coming up, please? Thank you. And the one that's not looking at me. You can bring your friend with you, okay? So 2 of you come on. Okay, now I want both of you. Come on, it's only for a minute. It's not too dangerous, I promise. Okay, will you put on those two gloves? And you put on your gloves as well. Okay, and can we have four glasses?
Gloves here.
Okay.
There.
And put on one.
Yeah, they're too small.
Are these too small? Yeah,
camera.
put on two of those. And then head up to the stage side there. And there's your okay. Fair play. Now, I just want you to put on two pairs of gloves. Yeah. Okay. So put on. Okay, put on those, and then you put on those. And take glasses off. Now, follow me up here. Now, really lovely. Give them a round of applause.
Okay, for him. So if you want to, yeah, if you just take one cup each.
Put your glasses on. Okay, so everybody take a cup each.
And
Here we go. Okay.
now, in one of these days, so if you pour what's in that into the cup.
Now, what do you think they're going to make here? Does anyone have any ideas? Nappies? I'm not sure. We'll have to wait and see.
Now if you want to take a dropper there, and drop in maybe a couple of drops of where you want, green or red, up to yourselves.
And then turn and face your classmates and show them what exactly you're going to be making up. And then you have to...
Just a couple of drops.
That's fine. A few drops is all you need. You can put it on the table, it's okay.
Okay, is everybody on that? Now I want you to take another dropper. And I want you to add 3 drops of what's in the beakers. Just tip it and just drop. No, sorry, drop in the whole lot. Just, yeah. Okay, and then you take a stir and start stirring. So, yeah.
The whole lot?
Yeah.
Okay.
Okay.
So you can take your wooden stir, turn around and stir away.
See?
Turn around. Okay, so...
What's next? So as you can see, we are what we're making in slime. So the 2 ingredients we're using is PVA or everything or PVA glue, and it's something called borax. And when they come together, it's very much like the nylon. The 2 start mixing together, and we get this polymer, which is kind of, as you can see, it's kind of stringy and gooey.
So I think...
we've got the bag, so you can bring that.
Yeah, you can take them all home with you if you want, okay? It's safe enough, so give them all a round of applause.
So, go on to the next.